Okay, this is Navika Academy, and we want to do some work on group theory. We want to introduce the concept of identity. We want to introduce a concept of identity. Concept of identity. Remember, when you are talking about group is actually under what you call algebraic structures, which of course are defines a pair of given non-empty set G defined with a given binary operation. So in this case here, if you want to define the identity of any given set, we need to know that we say that we say that a given E is the identity element for a given binary operation, say star, if for all G in a given non-empty set G, then G by E will be same as E by G, which is exactly G. So if this rule is satisfied, then you know that this particular E is the identity of that is the identity element of that group or that set. So this tells us, if we can look at some examples about elements which behave so, you find that 0. If you have a given set G and addition, I'll find that 0, this element here, will be known as additive identity. Okay, more so in these groups and integers, and again under the rational group addition, real numbers, and I believe also in complex. That's one. Secondly, if you have zero matrix and a matrix, zero matrix will also become the additive identity. In a given matrix n by n in real set, and 1 will be a multiplicative. Now in this case, multiplicative. It's a multiplicative identity in all natural numbers and multiplication. Now, this gives us leads us to the question that if we can ask ourselves this question: can we have a multiplicative semigroup or a group in which one is not a multiplicative identity? can we have a semigroup? Because a semigroup is also an algebraic structure, or a group point for that matter. A group point in which one, as we have just mentioned, is not the multiplicative identity. So if you pose that question, it will mean that we will need now to look at let's keep thinking about it. Of course, you can leave some comment down there in the comments box, and if you have not yet subscribed to this channel, just kindly subscribe, because we'll be looking at very more important discussions here. For matrix again and multiplication, we have what you call identity matrix, which is defined as along the diagonals, and it will find that it will be 1 if I is equal to j, but 0 if I is not equal to j. So that is what you call the identity matrix. Call that one identity matrix. So what you need to note keenly is that not always that the identity matrix, the identity element will always be zeros, ones. No. This depends on the definition, or actually the defined binary operation. So not always that the identity element will be 1 or 0. Okay, this depends on operation, defined operation. This purely depends on defined operation. So you have to note that. So that if I have this kind of example here, that you are told that relate this definition here such that AB is in that defined the operation on R squared by, say, A, B, okay, C and D equal to ND plus BC, FC plus BD. So here we need to show that the operation here, the band operation here, should define as so is commutative. It's both commutative and associative. Here the identity the indent element is E equal to 0, 1. So that if we can show we have this identity here, we can see clearly, you can show clear that if you take A, B, and we do it by the identity, by divination, we have A0 plus B1. Remember, we are here, this operation here, we are just following the definition here, and just doing direct substitution. So we're just doing direct substitution of what we know. So it's nothing to think deeply. Okay. So this one is giving us MB. Let's change the operation 0, 1 MB. And we see how this is BV plus 2A minus A0A plus 1B. Okay, this gives us AB. So you can see both are same. So because I've shown two signs of this, clearly you can see that this operation is both its own, it's both associative and commutative owns in this case. So it will mean then, that if we suppose we have a given structure, algebraic structure, whereby it has an identity, so you have just defined identity element, and it happens, which is E, and it happens that X by Y, which is same as Y by X, we get identity, then this particular Y will be the inverse. It's the inverse of X under the binary operation. So this is very key to note, that if this happens, we get identity for X in G, then it will mean that this Y is the inverse of X. It's the inverse of X. So at that point, we have introduced two concepts here. Two concepts introduced. One, identity. Two, inverse. For inverse, we have said that if you have a given E and E, then we get Y, and we have X, Y being equal for inverse, being equal to Y equals X, because that's allowed, and we get E, then that one will have defined the two concepts. So to this point, if you have not really subscribed to this channel, kindly subscribe. If you have a question on a given concept that you have introduced here, kindly leave a comment. I'll be able to check on it. So this means what? It It means if we are looking at this algebraic structure here, of Z, to mean here the identity for this one, by what we have said, is 0. Okay, and its inverse automatically of a given m in Z to mean that it will be basically negative m. It will be negative m. That's the inverse. That's one. Secondly, if you are talking about a given matrix, then we know the identity matrix is the identity. We know that from what we had just said earlier. Then its inverse, the inverse for A in the matrix group, or that algebraic structure, will have inverse, which will be, if there's a condition there, if the determinant, this is now borrowed by linear algebra, if the determinant is not equal to 0, then its inverse will be equal to 1 over determinant of A. Determinant of A times the adjoint of A, and matrix of A. We know that. And the 3, if we have this group here, of course we have removed, okay, 0, so it means that 1 is the identity, and if the m over n is not equal to 0, then it will mean that R inverse will be equal to n over m. That's for true. Yeah, it will fall like this. That's not true. Rationals. Okay. So if you have not subscribed to this channel, kindly subscribe, and you make sure you share with your friends. As I've just said, this is the Davika Academy, and we have been looking at different parts of mathematics, pure and applied, because we love maths. If you love maths, kindly subscribe.